Hi, thanks for joining. This is a brief talk about functional high-entropy alloys, and focus is placed on multifunctionality, on magnetic, Invar, and sustainability aspects of these interesting materials. The first question is, why do we assume that high-entropy materials are at all suited candidates for reconciling multiple functions in the same material? We can go back to the basic thermodynamic setup first of such materials, which consist in combining several alloying elements, as is well known in this field. And the main target originally of the high entropy concept was to stabilize by the high configurational entropy, also called mixing entropy, stable solid solutions, as shown here. Now, an alternative is that thermodynamically, it is very likely that at lower temperatures, many of these mixed materials might undergo a spinodal decomposition, such as shown here, which of course is a feature that can be exploited, for instance, for producing certain magnetic feature or for enhancing the strength of the materials. It is also conceivable, and has been shown before, that you can, according to the Gibbs phase rule, stabilize several coexisting solid solutions, which in themselves might have also high entropy properties. Some of them might also be rendered metastable, which provides avenues for designing mechanically very strong materials. And a classical observation that is very often made in this field, of course, consists in the fact that you form stable intermetallic precipitates. Again, that is sometimes unwanted when you only want regular solid solutions, but it can be also a very interesting material design tool. The main problem when it comes to rational alloy design in that context is the very high amount of possible states that such a material can assume. When you look, for instance, at the partitioning function and consider the number of atoms in an 8n dimensional configuration space created by not just the atomic positions, but also by the large variety of the chemical species and the respective spin states and electronic excitations, etc., we realize that the number of configurations becomes so large that this space cannot be conquered and explored with classical forward simulation tools. So that leaves us with a certain challenge. And we see that challenge not only in the design of the so-called classical high-entropy solid solutions, which reside here in the center of the high-dimensional phase diagrams, but we also see that increasingly, as you can see here on the left-hand side in this little movie, at the corners of high-dimensional phase diagrams. And the reason for that comes from the use of recycled material for the synthesis of new materials, because that means that you have typically a very high intrusion of contaminants, of impurity elements. And here you see, for instance, in this little animation movie, the aluminum alloy that has been made from aluminum scrap, which is meant to be relatively pure, but when it is made from recycled material, can contain up to 15 or even more impurity elements. And that means the analogy here to the high entropy field is that at the corners of these phase diagrams, we have huge numbers of elements often to consider also. So that means we talk both about the centers of these high dimensional phase diagrams, but also about their corners. Now, what is very interesting in that context to consider is that the entropy function, the mixing entropy function, which is an x ln x plus 1 minus x ln 1 minus x function for two components, for instance, otherwise it's a summation over all of these terms, is a very flat and rather unexciting function here in the center of these phase diagrams, as you can see here. However, when you take the derivative of this function, then you have singularities that go to infinity at the values for near 0 and near 1 for the concentrations. And that means, translated to the energy gain that when you blend very tiny amounts of alloying elements in these systems, like happening in materials made from scrap, for instance, then you have an infinite energy gain, and hence it is very, very difficult to clean recycled alloys. So that means the entropy function, the configurational entropy function, is particularly interesting at the corners of phase diagrams and not so much in the centers of phase diagrams. So this is just one of the big differences between these two scenarios, namely high-dimensional phase diagram corners that we need to consider for the world of recycled alloys versus classical high-entropy alloys in the center of these phase diagrams with this rather unexciting entropy function shape. And then we of course have to consider that we do not, with material science, live in the bulk alloy thermodynamic design, but real materials are characterized by a very complex cosmos of lattice defects, starting with all these surface features, which again can be attacked by real environments, be it oxygen or be it hydrogen, etc. We have cracked surface features, we have crystallographic textures, grain boundaries, heterointerfaces, precipitates, dislocations, substructures, and so on. So that means all of these also attract specific elements and trap them, a feature which is called segregation to lattice defects. But also this field becomes relatively complex and interesting and amenable to compositional tuning when we understand that in high entropy alloys, in massively mixed alloys, or in recycled materials with their many element types, the number of elements that are segregating to these defects becomes also very high. And that means we do not just have classical regular solid solution segregation like coined in the classical Gibbs adsorption isotherm, but what we really encounter is a phase diagram at low dimensions behind each of these defects. That is shown here in this diagram and was recently published by a couple of colleagues who have shown that when you then do no longer take the temperature and concentration to indicate areas in the phase diagrams and use instead the chemical potential of the different compounds like shown here, you can describe phase diagrams for the different dimensionalities of the respective underlying defects. So all of that can also be considered as, if you want, a high entropy thermodynamics and kinetics residing not only in the bulk but also at the respective lattice defects. And that can be very interesting for tuning properties, for instance in magnets for coercivity or in thermoelectrics for phonon scattering design. Now let's a little bit roll out what we can do with all these compositional features. It has been shown before for classical high entropy alloy design that you have, due to this massive mixing of elements, a number of mechanisms and effects at your disposal to design specifically certain structural and mechanical property features, many of which are named here. You see, for instance, compositional tuning for stacking faults, spinodal effects for the misfit that then create certain microstructural or strain hardening effects like shown here on the right hand side or on the left hand side when we tune them for certain mechanisms such as twinning, martensite formation, precipitate formation, and so on. And that creates a wide variety of possible type of complex alloys that we could then, for instance, coin TWIP high entropy alloys, which stands for twinning induced plasticity, or TRIP high entropy alloys standing for transformation induced plasticity, like raging high entropy alloys, metallic glass high entropy alloys, and so on. That means you can, with this concept, really reconcile the best of all worlds and have the advantage that due to the high solid solution ranges as a function of concentration, you can fine-tune many of these features like the stacking fault energy or the martensite transformation point and so on as a function of concentration in a very seamless manner. And that makes this high entropy alloy concept really a very flexible material design tool. On the other hand, what we have maybe neglected a little bit in the past is also the interesting opportunities offered to tune additionally functional descriptors. And I have named here a few, as for instance the magnetic moments, because if you take for a moment only the Cantor alloy family, which describes alloys pertaining to the group consisting of iron, chromium, manganese, cobalt, and nickel, for instance, you have in one single alloy the strongest ferromagnets and the strongest antiferromagnets together. That means there's, of course, a lot of room for very interesting magnetic moment design, and also for domain wall pinning, magnetic domain wall pinning, which is essential for tuning the coercivity when you, for instance, want to make soft or hard magnets. Likewise, electrical resistivity, or Cooper pairs for type 2 superconductivity, phonon scattering for thermoelectrics, and so on. And on the other side, you can then tune specific parameters like coercivity, the domain size, figure of merit for thermoelectrics, catalytic effects, so you can look at the corresponding volcano plots for these seamlessly alloyed ranges, and so on. And when we combine that with the enormous wealth of mechanical features and structural features that I've mentioned just before, we can target something that we call multifunctional high-entropy alloys, where you can bring some of these aspects together. Because we know nowadays in products, not only a singular material feature is often required, but rather a combination of some of these features, and often electrochemical features, functional features, and mechanical features come together. Because these materials must withstand not just a certain mechanical load, but also they are used in a corrosive environment and yet must maintain their functional properties like electrical conductivity or catalytic performance. So that is an overview diagram that shows the enormous wealth of possibilities that can be unleashed here. And we find that also reflected in the literature. When you look at the literature, you can see that there are multiple such combinations between applications, properties, methods, and these different high entropy related material classes. And that is also the context of the current presentation. That means the answer to that question is yes, the wide solid solution range specifically, which is suited for tuning bulk and defect states, also enables us a little bit better than in classical alloys to reconcile multiple functions in a single material. The second question, can multifunctional high-entropy alloys really compete with existing materials? Let's dive a little bit deeper into this. I've already mentioned this alloy family that makes use of nickel, cobalt, manganese, chromium, iron, and so on. And we can see here the tons of carbon dioxide emissions per ton of material produced. And that has to do with the underlying heating and melting conditions, but also particularly with the intrinsic and hard-to-abate redox equations that often make use of fossil reductants to extract the metals from their mineral ores. And you can see for iron, that is about 2 tons of carbon dioxide per ton of iron extracted. And due to the high amount of steel produced per year of about 1.9 billion tons, we have this enormous contribution of the iron steel sector to carbon dioxide emissions. But when you look now for small quantity material volumes produced, like for instance on the basis of this alloy system for making, Cantor type variants, you see that some of these elements like nickel or cobalt or chromium have even a much, much higher carbon footprint, depending very much also on which type of minerals are used and which type of processing is used to make them. But that means we have a substantial burden associated with the manufacturing of such high entropy alloys, and that must be taken into consideration also. Otherwise, there's no chance to bring them really closer to market. And as I've mentioned, as you see here, that has also to do with the quality of the minerals that stand behind the metal production and extraction. When we go through the periodic table and screen that for a couple of different alloy variants, then we can see indeed that many of the elements that are really interesting for the high entropy alloy design concept stand for very high prices, very high carbon footprint, and likewise very high energy footprint values. When we compare these high entropy alloy families that have been well studied and are very well known, like here the iron, manganese, chromium, cobalt, nickel system, or here the niobium, tantalum, titanium, vanadium, tungsten system, and so on, or some of these variants that might come into the play when it comes to the use of catalysis, then we see they will find a very hard time to compete with materials such as steels or aluminum alloy, so when it comes only to strength or corrosion features, because then these established materials will be very hard to beat and yet have also a much better carbon and energy footprint compared to some of these high entropy alloys. That means the design endeavor must always aim at taking us from the right upper corner down to the left corner, which amounts to reducing the carbon dioxide footprint of a certain alloy and likewise the energy footprint. This is very essential to consider. Otherwise, we develop alloys only for publications but not for real life. And that should not be the case. And these boundary conditions also translate in the metal price as a function of the relative abundance in the Earth's upper continental crust. That means we should primarily aim to use elements from this group when we make new alloys. And the point is not always that we use in part in the high entropy research area elements that are extremely expensive, because that is in principle tractable to handle by industry and manufacturing when there's a corresponding value in the properties resulting. But what is very hard to handle is when these materials, like nickel here as an example, are traded, because then we have extremely high spikes in the price, and that makes it very hard to handle this. And hence, this is a showstopper in that context. That means the answer to this question is that we are dealing here with very expensive, volatile, and unsustainable alloying elements. And that makes it very hard to compete with existing alloys that are worse. That means when we want to compete with these materials, we must compete with such materials that are also currently making use of very expensive and unsustainable elements like magnets, catalysis, or Invar. So that means, in other words, we should, with the high entropy alloying concept, try to target materials which have extremely good functional properties, but currently are produced also from very unsustainable resources. And that might be a real interesting niche for developing new materials. Let me show you one example, namely soft magnetic alloy design. This is one example of such, a phase and structure and feature map when you start embarking on this area. And like I've shown in the first slides, there's a wide range of solid solutions in which some of these features can be very nicely and in a seamless way being tuned. This is just something like a map, a treasure map for a possible playground when you aim to design magnetic high entropy materials. And what is very interesting when it comes to differentiating between soft and hard magnets lies in the coercivity design, which consists in stopping or impeding the domain wall, the magnetic domain walls, by microstructure features. And that would qualify a material then as a hard magnet, while letting the domain walls pass across lattice defects without much dragging forces qualifies them as soft magnetic materials. That means, in other words, the feature that spans up the hysteresis curve of a magnetic material, namely the coercivity, is a very microstructural feature that can be optimized in the high entropy world. Here is an example where you see the iron, cobalt, nickel, tantalum, aluminum system from this publication, where we indeed were able to tune the magnetic properties, namely for establishing a very, very mechanically strong soft magnetic material. And the basic approach consists in creating nanoprecipitates, as you can see here, of L12 crystal structure in otherwise an FCC matrix. And you can see here that depending on the heat treatment, you can create very different dispersions, sizes, and shapes of these nanoprecipitates, and also, as a function of the annealing time, tweak and change their respective chemical compositions. This is then very important for tweaking both the coercivity in terms of the interplay of these domains, L12 domains, with the magnetic domain walls, and likewise with the magnetic moments, which depend on the chemical composition of the respective matrix composition. And it was very interesting to see that there's a sweet spot, a crossover point for a certain size and heat treatment of these particles, where you see on the right-hand side, in terms of the red line plotted, the intrinsic coercivity. That means this goes down for this distribution function. That means this qualifies a material as a soft magnetic material, while at the same time the nanodispersion was very effective in making the material mechanically very strong. And that was the assignment of this material design, where we tried to reconcile multifunctionality in one material concept, including resistivity, strength, elongation as a measure for ductility, but also saturation, induction, coercivity, and so on. So again, that is just one quick example to show how such multifunctionality can be reconciled together with mechanical properties. Another very recent approach was also to not just create nanoparticles and tune them in terms of the dispersion and size, but also change the shape of these nanoparticles, as you see here in the atom probe analysis. And you see here also from the STEM HADF image that you can tune by precipitating some of these L12 particles along the dislocation course, very elongated shapes of these particles, which again has big advantages for very effectively changing the mechanical properties while not impeding the motion of the domain walls. And that enabled us to make a mechanically extremely strong soft magnet, as you can see here, with many different heat treatments, allowing you to tap into very different combination of these material features, which particularly allowed us to make a soft magnetic materials with an engineering stress of 2 gigapascals, which is, as you know, much stronger even than most steels. And yet we were able to maintain the soft magnetic hysteresis curve that you see here on the right hand side. And that shows in this overview diagram, where you plot the yield strengths, elongation to fracture, or also here the yield strengths as a function of coercivity, allowed us to create a completely new material that is far beyond of any material property combination that we have seen in the literature so far. And again, that is an example where you can use this high entropy concept for seamless composition tuning, for magnetic moments, for coercivity, and so on. Another question then is how to solve the curse of compositional microstructural dimensionality. I've already mentioned in the beginning that this composition space is practically infinite. And let me give you an example from the world of Invar and Invar alloys. These are alloys that have a very low thermal expansion in a certain composition range. And that was awarded with the Nobel Prize, for instance, in 1921 to Charles Guillaume. And here you see this very nice diagram from his original Nobel lecture, which shows the sequence of height of the Eiffel Tower as a function of day and night, so as a function of temperature, obviously, that he was able to measure with his new Invar alloy, the classical one being an iron 36% nickel alloy, in reference to the thermal expansion and shrinking of the entire Eiffel Tower. So that's a very exciting document to read, by the way, for material scientists. So what we did in order to compete with this since 100 years established alloy and find a new one is to start from a very sparse database. The problem is in the area of Invar alloys, there are not so many alloys so far invented. That means the starting database was very sparse. And we only took a few relevant data, here colored in green color, and trained the model with this initially very small subset of labeled data. And in each step of that loop that I'm going to show you, we enabled it with new labeled data. And for that, we used it for model predictions, but also enriched these model predictions with additional, quantitative approaches like DFT calculations and thermocalc calculations. And then the machine, the model, suggested us which unlabeled data set to pick next, and through the use of an oracle user to decide which is the best suited data set to then blend in the next loop as a relative data set to enrich this sparse database. And the oracle in that case has essentially been the researchers themselves to provide a high quality oracle process here. So that was an active learning cycle that we developed, and to identify stepwise high quality data to feed into that sparse database. And When we are a little bit more specific on the technique side, we started, as I said, with this very lean Invar database from the literature and developed this adaptive design loop in a way to first subject the data to an autoencoder, where we first looked whether an autoencoder approach is capable of identifying sensitive enough the different compositional groups. And as you will later see, that was indeed possible by using the Wasserstein autoencoder. And then we did a neural network and different boosting tree algorithms to derive the corresponding models. And as I said, those were also enriched by physical forward models coming from DFT and standard thermodynamic calculations. And then with these candidates, we went through a ranking policy of, plausibility and quality and corresponding feature analysis. And then we picked a few of them to really make an experimental validation. That means we cast the alloys, produce the alloys, subject them to PPMS analysis for magnetic properties, for Invar properties, and so on. And then added these new data in a feedback loop to the database. And then through this, active learning, we went several times in this through this adaptive design loop, and that allowed us to come up with new alloys. And here I could show you, I showed you, as I mentioned before, the Wasserstein autoencoder, the latent space representation, where you indeed can see that different alloy groups nicely show up. That means the autoencoder is capable of picking that up. And also when you do subtle variants, like we did here with the copper doping of this, near Invar composition, you can see that the autoencoder is indeed picking these different material clusters nicely up. That means there's a compositional sensitivity of this type of autoencoder, and that has been tested in these processes. And on this slide, you can then nicely see how we were indeed able to develop completely new covar in Invar alloys that can beat, as you can see in this over diagram, the existing Invar alloy families by far, like here plotted over the TEC versus configurational entropy. That means we have indeed successful artificial intelligence strategies at our fingertips for conquering this huge composition, microstructure, and processing spaces. Now, how can we improve on price and sustainability? That was one of the burden I have emphasized before. And here we have very recently only come up with a new approach. When you think about our classical tradition in alloy making, in alloy design, since more than 6,000 years, we typically first have the step of metal extraction by reduction, and that lends back to the point I made before, producing a very high carbon footprint for many materials in the first place. And then we have typically something like liquid alloying, where we put the different elements according to the desired stoichiometry under consideration of the vapor pressure and so on into vessels, where we mix them to achieve certain alloy compositions for steel, aluminum, or nickel alloys, and so on. And then in order to equip them with the required microstructures that later produce the properties we seek, we do very expensive thermomechanical processing, essentially heat and beat, to provide them with a certain grain structure, dislocation substructure, phase distribution, and so on. And then we have our bulk alloys with the desired microstructure, and particularly also with the desired properties. Now we have developed a completely new, quite revolutionary step here, that we say, why can we not take the oxides directly and subject them in a single vessel to reducing atmosphere, where the diffusion and reduction occurs simultaneously, but for some of these materials maybe in a stoichiometry, that means mixing the oxides in a stoichiometry to directly arrive at the desired bulk alloy. And that is a new approach that we tested out on a nickel iron example, again on an Invar example, which is a comparably simple binary alloys, but could serve as an example how to make such alloys in the future in a much more sustainable and cheaper and particularly carbon-free way. That means the main advantage is that all these reductions can be done in a so-called direct reduction way. That means in a solid state without making the material liquid, which of course saves a lot of time, money, and energy. And it can be made in a single process, in a single step, just in one reactor with less heating and less intermediate cooling and so on. No fossils are involved because we can use, for instance, hydrogen as a reductant, at least for many transition elements, which produces as a byproduct from that redox reaction set the water instead of carbon dioxide. And of course, you have much less capex, that means capital expenditure, when you design the corresponding workflows in industry. And from this example, you indeed see when we charge iron and nickel at the corresponding oxide stoichiometry into such a reactor, we indeed arrive at after a certain time at the ready-to-go Invar alloy, where of course you must make sure that the porosity from the powder mixture is closed due to creep and surface diffusion. And when you cast this into a certain pressure map, you can see here on the left-hand side the iron to element mixing enthalpy plotted, which tells you whether we will encounter more a solid solution, high entropy type of system, or whether we will encounter a two-phase or multiple phase type of decomposition. And on the right-hand side, you can see the Gibbs free energy of the oxide minus the Gibbs free energy of the water, which tells you whether these elements, are accessible to hydrogen-based reduction or not. And that shows you certain sweet spots of materials that could be tested out in such a procedure. And on the right-hand side, you see a similar map, but pertaining to some of the kinetic features where you want, as I said, in the same reactor, equip the material with a certain microstructure, and that must of course be considered also. What was very interesting to learn when doing these experiments also in situ, directly under hydrogen exposure in the synchrotron, then we could find that you have a gradual change of the lattice parameter of the nickel as it is created. Because when you make nickel oxide and iron oxide and subject them to hydrogen, then you can see that you, in the thermodynamic sense, you first create pure FCC nickel. However, on this diagram, plotting the lattice parameter as a function of the holding time in the hydrogen atmosphere, you can see that the lattice parameter of the nickel is changing continuously. That means it is possibly alloyed. And indeed, we later could find out and prove by that what happens in the reaction chain, the nickel oxide is the first oxide that is reduced by hydrogen. That is producing tiny droplets of pure nickel. And then what happens is that the remaining iron oxide, which is a little bit more sluggish to be reduced by hydrogen, is not waiting to undergo the complete reduction due to hydrogen, but some of the iron is starting to partition right into the existing nickel. That means there is a reduction mechanism that works without any fossil or hydrogen-based reductant, just directly by the partitioning and entering of the iron out of the oxide into the metallic nickel. And that is seen here in the change of the lattice parameter. So that also showed us a new reduction pathways where the iron-nickel Invar alloy comes out directly without any melting or complex processing steps. That means, yes, we can improve on price and sustainability of such at least transition metal high entropy alloy systems, where we use only iron nickel now as a demonstrator, through what we call a one-step direct synthesis from oxides to bulk alloys. And that can work really without the fossil reductants. So with that, I come to an end, and thank you very much for listening to that presentation, and leave on that last slide a little summary of the different facets of sustainable and functional and multifunctional high entropy alloys that we have discussed in this talk. So thank you very much, and see you next time again.